Alright, welcome to a new day. So we're going to talk about two different things, a little bit more about memory, and then also how computers start up. But I do not plan on testing you on either of these topics because it would just all be memorization questions, and I don't want to ask those of you. So yeah, just sit back, relax. These are things I'm required to teach you, but I will not be testing you on. So yeah, let's start with memory layout. Well, let's do it. So here is a picture of what physical memory looks like. We know that virtual memory is a thing now, and we cannot trust what addresses our programs are actually telling us because they're not real. But here is what physical memory looks like what the addresses kind of map to inside of our computers. Okay, so this is a picture of that. Notice how, if we zoom in, there's a lot of addresses here. If I zoom in further and use an actual pen, which I think is the wrong size, have a feeling. Here is like actual RAM. Like these, you get these addresses for RAM, and then if you use these addresses, you're actually hitting the cache. And then if you use these addresses, you talk to them in memory, just like read or write to them. You're talking to your keyboard or to your mouse. These are your peripherals. Some other peripherals that I don't really know what it's talking about. You can ask about your cache in either of these places. And then you can also get at like your graphics card. Like you can talk to your graphics card by writing to memory. Interesting. These are addresses that when you write to them or read from them, you're not actually hitting actual memory. You're hitting something else. And this is like the greatest thing that we ever decided to do in a computer. All right, we're using a lot of addresses, and when we talk to those addresses, we're not actually like storing data there. Maybe we are. We're like getting stuff, but we're not actually talking about RAM anymore. There are more addresses than there are bytes of RAM, first of all, if you look into all these things. Or maybe not. I think we'd have to like zoom ours out a little bit more. So I think this is exactly 8 gigabytes, which we do have technically, but like we're using more than that, all right? We're using addresses for more than just RAM, and I think that's the coolest thing ever, okay? So I think this is an example, honestly, of like a 32-bit machine. If you can imagine, like this is a 35-bit address map. And so these digits, right, correspond to like a 32-bit machine almost. Let's pretend that we're living in a 32-bit machine for a second. If we had 32-bit addresses only, we could only use 8 hex digits. That corresponds to 32 bits. And that gives you access to, and this is, right, remember that hex is base 16. That gives you access to like 4 zeros all the way to 4 Fs. And this is already past that. Okay, that's kind of the idea. Like you're writing to places that are farther away in a 64-bit machine. So 32 bits gives you the ability to talk about 4 gigabytes of RAM. You double that to 33 bits, it gives you access to 8 gigabytes of RAM. Okay, so this is still fine considering our class server, which has, I think it has 8. It has about 8. So that's perfect. So it's still, like this image is correct. Like if you go up here and use this 4 here, that's still way more than we actually have inside of our computers. That's perfect. Okay, so yeah, this is a really cool abstraction. It's when you turn your computer on, like the motherboard or whatever, if it's like a smaller device, like something on the chip is going and looking for all the hardware on that chip and everything that's connected, and it gives every piece of hardware its own memory. All right, so like your mouse, for example, has an address that your computer can read from to see like which button was clicked. Your keyboard has an address that it can write to, and your CPU can read from to notice like, all right, which keys were just pressed. Isn't that amazing? And so like that's what happens, and it tells the CPU like where all those devices are by writing to some other chunk of memory that may or may not actually be in RAM. So yeah, just every device on your computer is accessed by talking to secret addresses that aren't part of RAM, little fake addresses. That's called memory mapped devices. Memory mapping to addresses that aren't actually part of RAM. They're doing different things. If you write to this memory, you're gonna like turn a light on or something. Isn't that amazing? Like that lets you do whatever you want now. if you're the operating system at least. You can write to this particular address and you know you're hitting this device. And then you don't have to worry about like all the intricacies of like sending voltage to that device in a certain way. Like, no, this is taken care of for you by addresses. So that is one of the coolest things that exists today in a computer. That's the abstraction that we've chosen, and it's really, really powerful. Okay? It's like your RAM, sure, yeah, we're using that for virtual memory and all that, but other things, we're using other addresses to talk about other devices. Okay? And so that leads into the idea of bare metal programming, which I can't really show you because we don't have like a physical device, but let me just give you like a high level example. It's like if you are the operating system, you write your own operating system, you run just that one program on your device. That leads to bare metal programming, where you have just one program running on your computer right now. It's in the unprotected mode. It's allowed to talk to any physical memory address. And let's pretend that's us. We're the operating system. And let's pretend that we have an LED hooked into our machine, and we know that it lives at this address. We're talking to it through this address, okay, in memory. And so if we write to it, that will like turn the LED on. If like write a 1 or something, it turns it on. And if you write a 0, it turns it off. All right. So just for fun, we're going to pretend this. When I write a program, obviously it's going to be running through the Linux operating system. I don't have that full control. It's not bare metal, but let's just pretend it is. And that's going to be the idea. I'll show you something interesting anyway. So here's the program, led.c. So I have to do some weird stuff to pretend I'm an operating system, but we're just pretending right now. We're going to pretend that we have access to this address, and that's where an LED lives. So if you were the operating system, you could do this. You could just make a pointer, just pretend it's a pointer to an int. Like this is the address where an integer lives, and that controls the LED. All right, that exact address. You've never hard-coded an address before because you never knew which place was which. Cool. So we can do that. If we are the operating system, we know the LED lives there. So this line will create that pointer, and then you can write to it. You can write to it, turn it on, maybe all ones, turns it on, 255. Why not? And then you can like look at it, like go to that address and print out the value that you see there. Like if it's greater than 0, it's a red emoji. Otherwise, it's a white emoji. But hopefully that makes sense. So this is the kind of thing you can do if you were the operating system. You could go to a hard-coded address if you knew that's where a device was and mess with it. All right, that's called bare metal programming. So I'm going to simulate that by using a weird compilation strategy. I'm not the operating system right now, but I'm going to pretend I am by using this little hack. All right, don't worry about it. It's just saying that there is an int here, and that's where I want you to put it. Linker. All right, so I have to also compile with this fancy thing. Like have to make a special part of memory to say, when I'm given virtual addresses, like make sure there's something here. Make sure there's an int there. All right. So don't worry about it. It's just me pretending to be the operating system. If you were actually bare metal programming, you don't need to do anything extra. Just write to that address. You're good to go. Okay. So yeah, for this example, right, we're going to pretend that our virtual memory is actually physical memory, just for fun. All right, just to show you that you could hard code addresses and write to them. If this was really bare metal, you just write to the address. That's it. All right, so yeah, I had to add this. Be like, okay, there is an int here, and I want you to put it in this special place, which is going to go to a special address. All right, and so that's me hard coding it then after I do that. And to actually compile this, I have to turn off something that's going to like mess up and put this address somewhere else. All right, so to compile, I need to say this: GCC, the -g I guess is not really necessary, but I have to say no pi, PIE. No pi at all, and then I give these two files, all right? And pi, PIE, stands for Position Independent Executables. So by default, when you run a program on an operating system, it's loading that program into any address in virtual memory, placed in random virtual memory locations so that you can't hack it very easily. We're going to turn that off so we can actually put something at a virtual memory address that I want to control, all right? Again, we're pretending that this is physical memory, all right? We don't want pi. No pi for us this time, okay? And so I'll show that to you. And then we can obj dump it to see like how the assembly is getting made, and we could actually look at that address, all right, being talked to, which is cool. So yeah, let me do this. It's actually going to give me a warning because like what I'm doing is so weird, but it'll let it work. It will still compile it. So don't worry, it made a program called LED, and I wrote to it, and we looked at our LED. Yay, so I turned it off and then I turned it on. Cool. So I wrote to a special address. Isn't that so cool? I think that's exciting. All right. Oops. So I would like to not do that. I like to do obj dump now. Can I? No, I cannot. Let's obj dump -d our LED compiled program, and let's watch it talk to this address. Whee! And so that it prints out like the entire text of the thing. If I give it to less, the command less, it will show me. So let's see where it's like dereferencing and setting it to 0 and to 255. Let's find main. I think I can search for main at least. Come on. Not yet. Not yet. Where's the main label? Come on. There it is. So there's main. And you see it. Somehow hard coding this address, it actually takes 2 instructions to get it in there. It's being loaded in the instructions, and the immediates aren't big enough to store it all at once. But there's the 8675 part, and there's the 3090 part. And that is going to be placed into the X0 register. See how it's left shifting it as it goes with this immediate? That's a really cool thing, like move, I forget what the K stands for, but it's the ability to move an immediate to some place in X0 and keep everything else. Maybe the K stands for keep, I don't know. Keep the 3090 that was there, but also like, kind of like OR it with this left shifted. So that's kind of cool. And then it's going to that address. Now that it has it, it's for some very weird reason, it's storing and loading it at the same time. Then it's putting 0 there, and then we should see 255 somewhere. So there it is, putting 255 in W1 and storing it and like BLing and stuff. So that's what's being compiled for us. That's pretty cool. All right, so that's us pretending to be bare metal. Like if you were an operating system, you could do this. If you knew that this was the address of like the LED on your chip, on your motherboard, you can write to it and turn it on and off just by messing with memory addresses. So that is very cool, very powerful. All right. So yeah, I don't have a ton of things. I want to give you time to go and work on your labs and all of your, your projects, of course. Those are going to take some time. So not too much left today. Let's talk about how computers boot and how they turn on. All right, so first of all, let's kind of define what kernel means, because I've been throwing that word around. I've told you it's just like the operating system on Linux, but here's a better definition. So the kernel, that's like the underlying operating system component of Linux, at least. The kernel is a special program that is like the core of your operating system, and it has complete control of everything. It can talk to physical memory addresses. It can turn those LEDs on and off. It knows everything, all right? So the only way for you to talk to the kernel in your program, because you are talking to the kernel through syscalls and things, that's the only way, actually. The only way to ask the kernel to do something for you through your user-level program is through a system call. All right, so like here are your applications. Here's the software that you write. It's interacting with the kernel through syscalls. All right, and the kernel is also in control. Like it has complete control over your running programs. It's telling them where to load, giving them virtual memory space and all that. And like every possible thing your program could ever want to do that does anything useful at all happens through a syscall. Just like writing to the terminal screen, writing to a file, opening a file, reading input from the user, anything, getting the current time, like all that stuff is a kernel level syscall. All right, go and ask the kernel very nicely, give me this information. All right, and then it's also in charge of all the hardware. Here's the hardware stuff. It's talking to the CPU and the cache and like messing with memory. And of course, we know that if we go to memory, we can access devices. So it's in charge of all those. So yeah, system calls are huge. They're our window into the kernel through our applications that we write, okay? So the kernel is like the very first program that's loaded into your computer as it's running, right? That's the very first thing you want to get loaded, because then it loads everything else. It loads all of Windows, all of the many programs that are on the class server, okay? All that fun stuff. So yeah, let's talk about booting. How does a computer boot up, all right? That just means start, right? Hopefully you've heard that term by now. But like booting is actually a shorthanded form of this word. It's short for bootstrap, which is short for the phrase pull yourself up by your bootstraps, which is supposed to not make sense, but we say it anyways. So it is paradoxical, and this is a good time to use that phrase anyways, because like if you need code, if code must exist, right? If code is loaded by other code, then who is the first code that runs on your computer, and how do you get that in there, okay? So that's the question I'm going to answer for you right now. So like the boot process. When you turn on your computer, it loads a tiny, tiny amount of code into memory. Like that's part of the, lives on the motherboard or something. There's a tiny, tiny bit of code that's getting running. And then that sets off a huge chain of events that lets your entire computer pull itself up by its bootstraps and eventually get the kernel loaded and running. And that's your operating system. It's eventually ready to go. All right, so that's kind of the idea. Let me talk you through the boot process on Linux with using the BIOS boot process. All right, so I know that there's a different one these days. The more common one on machines is called EFI. If you've built your own PC or you've installed an operating system, you've heard of EFI by now. But I'm going to talk about a simpler version. All right, the one that came before, and it's still in use today, but it's easier to talk about. All right, so this is the BIOS boot process for the Linux operating system. All right, there's always a difference. Okay, so the second your computer gets turned on, the CPU is designed to, it has like a hard-coded jump once it knows it has power connected to it. The very first thing it does is it jumps to a predefined address, because again, we're placing interesting things in addresses that aren't actually part of RAM. All right, so it's going to jump to a predefined address. It's going to like do a BAL to a certain address, a hard-coded address, and it's going to start running code there. And that is usually going to be part of the motherboard's code. All right, and so what happens is, it's where the BIOS is located. All right, which is short for Basic Input Output System on like your motherboard. So that is the address where it lives, and your CPU can talk to it. It's not actually part of RAM. And what the BIOS is going to do is it's going to like initialize itself. It's going to be like, okay, let's load some code to like notice the other things that are plugged into this motherboard. All right, it knows how to do all those things because it was made by the motherboard manufacturers. Like everything works in a normal way, but through addresses usually. And so it's going to initialize, it's going to test the system, make sure there's like RAM hooked in and all that, test all the hardware, and it's going to load a bootloader. All right, so the bootloader is like a piece of your hard disk. It's going to go into the hard disk. Like the BIOS loads enough drivers to access your first hard disk or whatever. And what it will do is it will find a little chunk. It knows that there's a little chunk on your hard disk in a certain spot that is called the bootloader. All right, so that will start reading some of your disk. All right, it's going to read your disk and notice what's there. Okay, and then that tiny information that was read off your disk, it will load more things, and then it'll load a slightly bigger program into memory. All right, it figures out what to load. Like then it goes and loads these things more and more and more. Slowly but surely, it's building itself up. It loads a tiny amount of code, that loads a bigger amount of code, that loads an even bigger amount of code, until like it knows about all of the devices. It's able to like load the starter kernel and get that going. Okay, so that's kind of the process. Okay, that's what's happening. And yeah, just like at the very start, when your CPU gets turned on, it knows to go look at memory at this address, like right here. Like that's where some code is going to be that sets everything into motion, which is really, really cool. It's just part of the motherboard. So yeah, there's a cool picture on the next slide. But the goal is like load enough code to eventually start the Linux kernel, find the rest of my hardware so that I can read from the entire disk and get everything loaded, get the entire kernel loaded, and start the very first program. Okay, so here is a good drawing example of what's going on. All right, so here's time from left to right. So things are happening. So like your hardware exists for the entire amount of time, of course. And then the very first thing that happens is when you turn your computer on, it's going to load that tiny, tiny piece. Like the BIOS, the motherboard's going to get started, right? The CPU gets everything started, and it goes to that special place that marks BIOS code, specialized BIOS code. It's going to initialize everything. It's going to talk to the hardware, figure out what's there. And then it's going to read a little bit. It's going to learn enough to get drivers and everything and like be able to read a tiny, tiny piece of your hard disk, your first hard disk or something. And that loads what's called the master boot record. Okay? And so it's talking to BIOS, like that's the wrap around the hardware right now. It's like it knows just enough to read from your disk, go to the master boot record, load a bootloader from there. It's a tiny piece of code. Okay? That's going to get loaded. That's going to try to load the rest of the operating system. So it's just more and more things get loaded slowly but surely. Still talking to the BIOS to like do the reading, access the keyboard and all that. The BIOS is in charge right now because nothing like the operating system hasn't been loaded yet. It's up to the motherboard. And then there's just like a bunch of stages, right? There's a bunch of stages that like get the kernel ready to go. It loads it into memory. Everything's happening. At the very start, all these things are happening when the CPU, by default, when you first turn it on, it's set to what's called real mode. And that means you don't have virtual memory turned on yet. Real mode means no virtual memory. If you go to address 17, you are getting the thing at address 17 in physical memory, the 18th byte, because they start at 0, right? So no virtual memory yet. We're just talking to legitimate addresses, and that will talk to hardware more or less. But once the kernel is more or less loaded, it switches the CPU over into protected mode. It hooks itself in to know that like it marks itself as it's the only thing that's allowed to talk to physical memory. It starts the process of getting virtual memory ready. The kernel finishes initializing itself, and then it's in charge of the hardware. It is straight shot to the hardware now. It knows about everything. It knows how to communicate. It's not BIOS in charge anymore. So it's got the full drivers all ready to go. And then it starts the very first process, which is, we can think of it as like the login screen or something. Like it's starting a program that like loads everything and gets us ready to log in as a user, okay? And so yeah, then it's able to talk to the kernel through syscalls and all that. Like there's a barrier between the user mode processes, which are just non-operating system things, and the actual kernel now, okay? So that's pretty much what happens. So yeah, protected mode is, it means that we have virtual memory now, which means we can load somebody else's programs and they can't touch anybody, any other running things. Like everybody's safe now. It's a safety thing, okay? So yeah, that's kind of how programs get started, and like that's how your computer turns on. It pulls itself up from its bootstraps, all right? You may have heard of EFI. Go and look on the Wikipedia page for that. It's just a fancier way to do kind of the same things. It's still loading a program and letting that eventually load the operating system. It's just slightly fancier. But yeah, this BIOS boot process is still a thing. It's still alive and well. So it's worth talking about one way or another. But yeah, that's really the lecture for the day. I don't want to like overload you with too much because I know that you're working hard on your projects, among other things. So go work some more on that, and I will see you later.